Uh, Hello, may I audible? I'm not sure if
Yes,
I'm.
sir.
Now any presentation is going on or it's okay?
Sir, sharply start at 2 p.m., sir.
Yeah, okay, okay, fine.
Thank
Uh,
you, sir.
okay, just one thing. Let me check whether my PPT can see or
Yes,
not.
sir.
So just can you stop sharing so that I can check whether my I can share my screen or not? Just to check.
Sure, sir.
Thank you. Is it visible here? Okay,
Yes, sir.
okay. Thank you.
Okay, sir.
Hello, Professor Nandi. Professor?
Yes, please, please.
Yes, sir. How are you? Yeah, sir. Thanks for joining with
Okay, no problem, no problem.
us.
How are you? May I audible
Delegates
properly?
and yeah, the Professor Nandi. Now I'm requesting our one of yes, Professor. Yeah, Professor.
So that I am asking, may I audible properly?
Hello.
May I?
Yes.
Okay, okay, okay.
Yes, Professor. Yeah, audible. Professor.
Yeah, yes. I can hear you.
Yeah, it is audible. No issue.
Okay,
Yeah.
okay. Thank you.
Okay, Professor. Welcome to the dear delegates and Professor Ganesh Nandi. Good afternoon to all. Now I am requesting Dr. Karthik, our faculty, to introduce our today resource person.
Thank you, sir, Dr. Suresh, sir. Good afternoon, one and all. So I am very happy to invite our resource person, RTC 2021 afternoon session, Professor Dr. Ganesh Chandranandi, PG from Banaras Hindu University, and he completed his PhD in Banaras Hindu University in the year of 2008 to 2012. Before that, after his PG, he joined as the Chem Biotech Research International Private Limited, Kolkata, for 1 year. He worked there. Then after his PhD, he went for as a postdoctoral in University of North Florida, USA, in the year of 2012 to 2013. Then he moved to as a postdoctoral fellow, University of Common in the year of 2013 to 14. Then he joined as the DST Inspire faculty. Sorry. After that, he joined as the DST Inspire faculty in CSR NIST Trandram. There he worked as January 2015 to March 2018. Then finally, he as now at present he is an assistant professor in NIT Trichy. In his research credit, he has more than 40 international reputed journals, and now he has guiding more than 4 students. So he has some 3 to 4 books chapters also. So I am very happy to invite our today speaker, Dr. Ganesh Chandranandi. Thank you, sir. Please welcome, sir. Now screen is yours.
Okay, thank you, Dr. Karthik, for your introduction. So just give me
Thank
a
you, sir.
second. Yeah, thank you. Just give me a second to upload to share my screen. Is it visible?
Yes, sir. It's
Okay,
visible.
okay, fine. Okay, fine. Just 1 second.
Yes, sir. It's coming.
Okay. Okay, now it is visible, right? Please tell me again.
Yes, sir, it's visible.
Okay, okay, fine. I just changed to my writing pad. Okay, thank you, Professor, for this introduction again, and thanks for your invitation. Uh, yeah, okay. So actually, I have been told that the webinar is primarily based on motivating the master student for the, for the research. So that they should come to the research. And as an organic chemist, I thought that retrosynthesis would be the best topic to discuss at this moment, as it connect the research and basic science very nicely, and also it discusses almost all parts of organic chemistry, mainly reagent, mechanism, name reaction, intermediates, almost everything. You can what are the, from retrosynthesis, what are the informations we are getting. So so just I am starting retrosynthesis today, and I hope that it will be very helpful for the audience present here, particularly the MSc students or some research scholars also, who are maybe first, second year for their research. Okay, okay, and okay. So as you can see, my slide, it's retrosynthetic analysis. It's mentioned here. Okay, so first I must acknowledge the book written by Stuart Warren and Paul White. Basically, it was earlier written by Stuart Warren. It's Organic Synthesis, a Disconnection Approach, and the Organic Chemistry book by Jonathan Clayden, Greaves, and Warren, and some journals. Almost all the examples have been taken from these books, and I have mentioned here. Okay, so first we should know what is retrosynthetic analysis. It is also known as antithetic analysis or synthetic planning backward. So from the name itself, retrosynthetic analysis, you can understand. So we are going through the backwards way. Okay. So the term was coined by Professor E.J. Corey for the total synthesis of a large number of naturally occurring and bioactive molecules. Around 1960s, he coined this term. In his book, The Logic of Chemical Synthesis, you can see his picture here and the book over here. Okay. So, and Nobel in the year 1990s for his contribution in organic chemistry, particularly in retrosynthetic analysis. Okay, basically he coined the term retrosynthetic analysis. Thereafter, working on natural product increased a lot. Yeah, that's the thing. And he developed plenty of reagents and synthetic methods. You know that Core chem reagent, Core oxidation, and yeah, plenty of new methods as well as reagent he developed. Okay, so what is the reason to develop this retrosynthetic analysis, or this retrosynthetic analysis, why this is essential? What is the necessity of this retrosynthesis? So first, we should know that the goal of organic synthesis, we, the organic chemist, whenever we are synthesizing some compound, always it is in our mind that the product, final product should be synthesized from a readily available starting material, cheap, and the process should be very efficient and convenient. Okay, it is the major goal. Now, earlier, you can see here, earlier many natural products, mainly quinine, cholesterol, cortisone, reserpine, etc., have been synthesized by many chemists, mainly by Professor Robert Burn Woodward. He is also, a done is natural product. Okay, so many natural products have been synthesized before Core started his work on natural product synthesis. But then now then, why this retrosynthesis comes here? It is mentioned, you can see here. However, this synthesis were performed more or less intuitively. Okay, synthetic planning was not formulated on systematic footing, so their planning was difficult to perceive. So basically, it is not like that before Core developed or retrosynthetic analysis, people did not knew about this one. People used to do maybe, but they did not coin the term how they are doing. But it is not represented in the article, journal, or paper. They are not talking about all these things. So what they used to do, the synthetic routes are developed by selecting an appropriate commercially available starting material, structurally resembling the desired molecule, and building the other parts of the molecule. suppose it is, I mean, from this line, suppose it is said that your target molecule is this one. Okay, so what will we consider? So we will consider, okay, this may be one of our starting material and this may be another starting material. Like that, they have okay, taken this one and this one. So this type of retrosynthetic analysis is not mentioned before Core coined the term retrosynthetic analysis. Okay, so the problem was that now this is very simple molecule, one can understand very easily. Now if the molecule is such big, very complex, it is really very difficult to understand. So here you can see here that, but the difficulty in recognizing the available starting material for many complex molecules called for a more systematic method for recognizing simpler molecules from which the required product could be obtained. Okay, so one systematic method should be needed so that anybody can understand, okay, how he choose the starting material. It is not like that randomly somebody choose ABCD, somebody choose XYZ, like that. So there should have a proper way, I mean, some kind of theory, you can say. They have proposed some theory through this retrosynthetic analysis. Okay, now this is the photo of Robert Burn Woodward. I just put this photo because he's a, I mean, great personality in the, I mean, for the natural product synthesis. The era 1940 to 1960s are called Robert Burn or Woodward era. Okay, so in this time he synthesized plenty of very complex natural product, and he received Nobel Prize in 1965, and he synthesized one of the very complex molecules, vitamin B12 there. Okay, so even before he tried all those complex molecules, people used to think that it is very difficult, or it is almost impossible, all those complex natural products. Okay, so he is the person who showed the world, yes, we can synthesize this very complex molecule. And also you can understand, in the year 1940s, that time almost there was no instrumental support that time. Okay, NMR was just started to develop, and many other instruments. So from that scenario itself, he synthesized plenty of molecules. And one thing I must tell you, he is the person, one of the pioneer person to use NMR, 2D NMR for organic synthesis. Okay, so yeah, I thought to discuss about this person itself. Okay. Okay, now here is a definition. What is retrosynthetic analysis? Although I have told, so this analysis is a problem solving technique for transforming the structure of synthetic target. Transforming the structure of synthetic target molecule to a sequence of progressively simpler structure along a pathway which ultimately leads to simple or commercially available starting material for a chemical synthesis. So basically it's nothing. Suppose this is your target molecule, you are breaking this molecule successively. Okay, progressively you are breaking the molecule in such a way, finally you will be getting the starting material which are commercially available, or you can synthesize this compound very easily. So this is the thing. Now you can see here the first notable example of a product being transformed into its synthetic precursor was that of Robinson's tropinone synthesis. I think all of you who are studying MSc or even in graduation also, they have seen this tropinone synthesis. Okay, so this is done through the double manic reaction. This product is synthesized. Anywhere you can see. Okay, so what he has done, see, if you see this tropinone, and you can see it has been broken. If you broke these two bonds, or you can say you can disconnect these bonds, you will be getting particularly these three compound. Okay, these three starting material. Now consider in 1917, did Robinson do the electrosynthetic analysis? No, but somehow he did this breaking, right? But actually we don't know he did this breaking. But anyway, now when one searching this molecule, or just one is doing some research particularly on this molecule, they can easily see that it is a simple disconnection can give you very available starting material, and in one step, only in one step you are getting this tropinone. So actually in 1917, when he synthesized tropinone, that time tropinone was, that World War happened, First World War happened in 1914. Okay, so during that period, one of the material, that is atropine, that was used for some nerve related disease. Okay, people used to, the in the war, some country used to use some chemicals which can cause nerve related disease. Protect or to prevent the nerve related disease, atropine was needed. Now atropine could be synthesized from the tropinone. Okay, so for this, tropinone was very much important. Now you can, this is one line, you can see in 1901, okay, in 1901, Will Steller synthesized tropinone following a 15 steps process which provided only 0.75% yield. So you can understand, already this compound was synthesized but only 7.75% yield. So it was very difficult to synthesize this component, even that is 15 steps. So you can understand. But when Robinson synthesized only one step, and all these compounds are easily available, readily available. So this is the, essentiality, or you can say the necessity of the retrosynthetic analysis. So there are some terms and definition of those terms. Target molecule, the molecule to be synthesized, retrosynthetic analysis. We have seen what is retrosynthetic analysis. Disconnection. So we should disconnect the bond. So basically this is the imaginary bond cleavage process. Okay, imaginary bond cleavage running to the reverse of a forward reaction leading to the immediate precursor. This is also known as transformation and is indicated by a wavy line. This is important. So consider if this is your target molecule, we are just putting a wavy line over here. So here we will be doing disconnection. So once we do the disconnection, we are getting here a negative. Okay, this is up to you. You can put a negative or positive. It's up to you. And this is a positive charge over here. You have, it's put it. Now, retrosynthetic arrow. So what is retrosynthetic arrow? Its disconnection is represented by a double line closed arrow. So double line closed arrow means this one, which indicates the transformation of the molecule into its immediate precursor. Okay. So obviously transformation of this molecule into its immediate precursor. So from immediate precursor, you can synthesize this molecule. Now synthons, what are synthons? Synthons are imaginary fragments. So as we told, and is also imaginary. So synthons are also imaginary fragments obtained by disconnection. Synthons are not real compounds. Obviously, these are not real compound, but are idealized ionic or neutral fragments, and they are not reagents. This is okay. Obviously, they are not reagents. Now you can see here. So these are synthons. These are imaginary molecule. Now, what are synthetic equivalents? You can see here. This is a benzene ring. We can we just wrote it here. So synthetic equivalent means from what compound we can get those synthon. Okay, like this NO2 plus is obtained from HNO3. We know how it is obtaining. How we can get NO2 plus from HNO3. Okay, so similarly from benzene, obviously we may not get directly. We need to do some reaction. Okay, from that we can get this. So get this phenyl anion over here. So these are called synthetic equivalents. From synthetic equivalents. So from the compound we are getting synthon, from whatever the compound we are getting synthon is called synthetic equivalents. Okay. There is another term, retron. Retron, this term is not basically widely used in retrosynthetic analysis. Basically, we don't need, but it's a minimal molecular substructure that enables certain transformation. So basically, it is presenting this structure is present in the target molecule that is obtained by the reaction of starting molecule. Okay, so you can see here is the target. So what is the starting molecule? These two are the starting molecule, and the starting molecule react with each other to give you this final structure, main structure. I can say, I would not say there are obviously these bonds are there, but the main this functionality they have given. So this is called retron. So similarly, this is your Diels-Alder reaction. One diene, another diene and dienophile. This is giving a 6-member ring with a double bond. Okay, so this is also a retron. In the same way, this is your Robinson annulation. So what through Robinson annulation, obviously it is happening through this one, this active methylene group, and whenever it is reacting with this one via Michael addition and followed by this reaction, you will be getting this product. So finally, what structure is forming? This one. So this cyclic structure we will say the retron for Robinson. For the Robinson's annulation. Okay, now there are functional group interconversion. It's a very simple. You can see here this is, if this is your target molecule. Okay, if this is on your target molecule, so how to synthesize this one? You can get it from this N protected N acetyl protected compound. So this is the N acetyl functional group, and this is amine functional group. So these two are different. So functional group interconversion. Again, this is not from amine to N acetyl group you are converting. So this is also functional group interconversion is happening. So in the same way, functional group addition. Okay. So some functional groups need the addition of a group to the immediate precursor suitable for disconnection. Suppose it is your target molecule over here. So from this target, how we can get this target molecule? You know, to get a double bond, one of the easiest way is the dehydration. Okay, so to get this dehydrated product, what we need to have, a hydroxyl group should be there. So when we are adding this hydroxyl group extra over there, we'll say that this functional group addition. So one of the functional group we are adding here. So this is called functional group addition. Okay, now come to the order of events. To see or to get to know about the retrosynthetic analysis, we should know that how we will disconnect the thing. Okay, how we will disconnect the structure. So there are some obviously there are some process. Now remember one thing, everything, if you wanted to understand properly, you need to practice. Practice is the main to understand the order of events or disconnection, which one you want to disconnect first, which one you want to disconnect later. But anyway, they just propose a theory or just give some proposal through which you can proceed. Okay, initially if you don't understand, suppose how you can proceed at all, for that some rules they told. Okay, so the first one is disconnections must correspond to known and reliable reaction. Okay, so obviously disconnection must correspond to known and reliable reaction, means you should disconnect in such a way that further reaction, if you do, that reaction should be known and it should be reliable. I mean, after seeing that reaction, you can understand that yes, this reaction I have seen some textbook, and so okay, this reaction can happen. Okay, it's not like that this reaction cannot happen. So suppose you have this molecule and you are disconnecting in here, it is mentioned here, but it's a bad choice of disconnection, no reliable equivalent reaction. How we can say no reliable equivalent reaction? So here it is a positive charge you are writing, and here it is a negative charge. Okay, suppose you are writing the opposite. Negative and positive. Suppose you are writing any of this. So positive charge on oxygen is almost not possible, right? Or even if it is possible, it will not be very stable. You all know this thing. Okay. So now this negative charge, again, a negative charge on that phenyl ring, people in general want to don't want to do this reaction. Basically, you need to have a Grignard reagent or something. Now you can see here chlorines are there. So this is not possible. We should remove this part. Now you can see here positive charge. Now here positive charge, what does it mean? So positive charge means there should have some leaving group, right? Consider it is bromo, and this is O minus. So O minus should attack bromide. So this is an aromatic substitution reaction. So in general, we are avoiding aromatic substitution reaction, you remember. Okay, unless if it is very much necessary, people always want to avoid the aromatic substitution reaction. So there is, so then if we cannot go through this process, what we should do, instead of breaking it here, let us break it here. So breaking here, you can see so nicely, yeah, it's mentioned here. oxygen becoming negative charge, you can put negative charge, and this synthan is made as positive. Means here you can put a bromine group here, so it can easily attack here and it can remove, and you will be getting your product. So disconnection must correspond to known and reliable reactions. So this is known and reliable reaction, right? Simple substitution reaction. Now, for compounds consisting of two parts joined by a heteroatom, disconnect next to the heteroatom. So, in a compound, if there is a heteroatom, okay, just disconnect next to the heteroatom. So, there is one sulfur atom, it's there. So, where we should disconnect? We should disconnect at the next to this heteroatom, this bond, we should disconnect. Okay. So, if we disconnect, what is happening here? You can see here we are getting these two synthan. One is S minus we can do, and yeah, here we can add any leaving group. Here it is mentioned chlorine they have mentioned. So in the presence of this base, we are getting this product. Okay. So for compound consisting of two parts joined by heteroatom, disconnect next to the heteroatom. It's done. Third one, it's really important and yeah, interesting. Suppose this is your target molecule. So it is mentioned, consider alternative disconnection and choose routes that avoid chemoselectivity problems. Often this means disconnecting reactive group first. Okay. So here you can there is a heteroatom, both are oxygen oxygen, and both these with both these heteroatom one groups are present. Yeah, some groups are attached over there. Now you can make obviously you need to break all these two bond, E and F, both these two are bond you are breaking. So once you break E, you are getting this product, and from this one again you can break, and finally you will be getting suppose you are getting this one, right? Because you also need to prepare this one, and then pH CH2Br. Okay. So in this case, if you are breaking F, it's a similar thing. First OH is forming here, then you are breaking. So finally you are getting, suppose it is Br. Okay. So both are all are similar. This in both cases starting are similar. Now the question is that which reaction you will do first? First you will do this you will attach this benzyl group with this oxygen, or this group with this oxygen. So that is the question. Now the thing is that, see here what people they have done, they have first attached this benzyl group. They have first attached this benzyl group. Now only one OH group is there, so it can react only one of this bromine. If you are using equivalent amount of bromine, so one of this bromine you can attack, and it will be giving you this product. And this is we no need to consider this one. This is some other product they have synthesized. Now suppose you are doing the reaction, this reaction first. So where that chemoselectivity related issues are coming, that's we are telling. OH, Br, right? We have we got this product, no doubt. Now again, even you treat it with this compound, then what will happen? There is a free OH here, right? And this is leaving group, this is also leaving group. Now along with this product, it is highly possible that another molecule of this compound can attack this bromine, and similar you can say that the polymer of this compound, okay, polymer of this alcohol can form, right? So this is, in this way there will be a selectivity related issues. So because of that, it is necessary you should choose routes that avoid chemoselectivity problem. Okay, I think it is clear. You please note down the this slide number if you have any problem later. Okay, now the fourth one, use two group disconnection wherever possible. So what does this mean of two group disconnection? Okay, so what is the meaning of two group disconnection? Suppose in a target molecule, okay, in a target molecule, if there are two functional groups, so you should disconnect in such a way the two functional groups should be in two different synthons. Okay, so what I'm telling, if there are two functional groups in the target molecule, you should disconnect or try to disconnect in functional groups should be in two different synthon or synthetic equivalent. So here this is your target molecule. Now you can break it through A or through B, as it is told that you should break the bond that is nearer to the heteroatom. Now if you are breaking through A, what is happening? You can get these two synthon, right? These two synthon you can get. So in this case, you can see here, and this one, if you are putting one, suppose bromine over here, then what will happen? If you are reacting these together, this OH can attack here, or this OH also can attack here. So there will be a problem of chemoselectivity. So chemoselectivity related issue will come. But if you are disconnecting here at B, you can see what product we are getting. We are getting this one. We are getting this one, and there is a positive charge we can put. OH we are getting here. Now this means what? We can put a bromine here, and it's just nothing but a epoxide you can put. Now you know that if this is epoxide, you can just attack here, and it will, this bond will easily open and will give you this product. Almost more than 80% of yield this will be giving very easily. So there is no chemoselectivity related issues you can find here. So it said that use two group disconnection wherever it is possible, and here the synthetic pathway they have, it is shown here. Yeah, this is NaH in the presence of base, O minus is formed, then it is attacking here to give you this target molecule. Okay, now we come to one group disconnection. So we are slowly going to little bit deep. Okay, so what is one group disconnection? One group disconnection means in the target molecule there is only one functional group. Okay, like that we should do. Now suppose it's a carbonyl derivative. Suppose it's a carbonyl derivative, then what we need to do, RCOX, carbonyl derivative. So X means it may be NH, it may be OR, or it may be SR, anything. So in all this case, what we need to do, we need to break this CX bond. Then what synthon we are, this is plus here away, and this is minus. This is acyl cation, yeah, and the synthetic equivalent of this molecule is this one. Add any leaving group over here. This is your maybe chlorine, maybe bromine, anything you can put. And this is from X, this is nucleophile. From nucleophile corresponding H will be there, obviously. We'll discuss. Now see the retrosynthesis of particularly this product. What we need to do? CO, this is an ester, COO. Okay, so what we should do, we need to break it over here. We break it. Once we break it, we are getting positive charge here. Now it is equivalent to either this chlorine or this anhydride. Okay, and this negative charge means this is alcohol, simply benzyl alcohol. So how to synthesize this one? If you treat this benzoyl chloride in the presence of base, it has been found that with pyridine they are getting better result. It's not like that with other base you cannot get this product, but with pyridine you are getting better yield, so that they have mentioned here pyridine. So you are getting this product. So in the similar way, suppose you have this compound over here. Now what to do? You need to break it here, obviously, right? So you are breaking it here. Two synthon we are getting. One is this one, another is this one. So you can easily attack here and you can get this product easily. Now just to show you that this compound may not be commercially available, you can synthesize this. So in general, this amine is synthesized via the reduction of nitro group. You can see here, first we need to take this nitro, or this nitro can be formed from this dichlorobenzene. I am not discussing this part, this is very simple. Okay, you can see any book, you will be getting. Okay, now this is one interesting example. You can see here there is two CO group, one is COH and this is COO ester. Okay. So what to what to do here? Obviously COO means we can break here. Let us see what we can do. See, once we break here, we are getting positive charge over here. Obviously it will be an alcohol. It's yeah, this is also benzylic alcohol. Now this synthon is equivalent to this product. So synthetic equivalent of this synthon is this one. You can see easily, right? From this O, it will attack directly. You will be getting this starting material. So once you treat this one with this, it will just attack here, and this bond will break, and you will be getting this final product. Very easy. This or this. So how to synthesize this one? In all cases, ROH, this alcohol is acting as the main precursor. Okay, so why we synthesize this one as the immediate precursor to get this sulfide and all? Because OTS, OMS or BR, these are very good leaving group, so that instead of reacting this one with this further alcohol or this thiol, all this thing to get the corresponding ether, sulfide or thiol, it's better to synthesize this molecule. In that case, you can get the better yield, okay, and reactions will be much easier to do. So that benzyl halide, suppose X means any Br, any leaving group, and this is a alcohol. And what we are getting here we are getting benzyl alcohol, okay, we are getting here benzyl alcohol. You can see this part and this halide. Now which one is better process to do? In both cases we can get the target molecule, right? Now the which process is better? A is much better than B. Why? In case of B, you can see here it will give you direct this product, no problem, but there is a probability that there is also hydrogen, right? So there is a probability that it will give you the eliminated product. There is a probability. So to overcome that problem, so let us don't use the starting material, let us use only these two starting material. So these are some common term or common thing we should check whenever we are doing some synthesis, okay. So these are the retrosynthetic term we need to remember. So from retrosynthetic study, we get to know about all these things. In general, this will be not in our mind always, but if we study retrosynthetic analysis, it will be always in our mind that how to disconnect a molecule so that we can get the perfect starting material, okay. One group CC disconnection. Obviously, in the final target molecule, there is one functional group will be there. So till now, what we have done, CH disconnection, C and heteroatom. Now we will be doing the CC disconnection. So first alcohol, okay. So any alcohol may be disconnected at the CC bond near to oxygen. So here what you can see here, so this is a alcohol near, we need to disconnect the CC bond near to oxygen. So either we can disconnect here, or we can disconnect here, or we can disconnect here. So as I already told you, or you know that if we disconnect here, this will be the positive charge. It is not very acceptable to do the aromatic substitution reaction. So let us just disconnect it here. So we are getting positive charge here, and positive charge means you can make it an aldehyde, okay, and this negative means it's simply a Grignard reagent, you can understand, okay. Now if you react these two molecule, it will attack here and you will be getting this product. It's a simple thing. This is your target molecule. So similarly, this is another process to synthesize this molecule, okay, yeah. So this is another process to synthesize this molecule. Instead of this bond you are breaking, you just break these two bond, okay. So charge here and one negative. This means this is your Grignard reagent. And what does it mean? It means it's simple epoxide, okay. So if you treat these two compound, you will be obviously getting this one in very good yield. So either you can choose this one or you can choose this one. But in general, it is said that if it is alcohol, and if your if your condition permits, I mean reaction condition permits, you must follow this method, okay. So if you follow this method, almost all the molecule containing alcohol you can synthesize, okay. Now here what you have seen, only with this alcohol only two groups are substituted, okay. Now suppose if all the all the hydrogens are substituted from this carbon. If there are two identical groups are there, then what we should do, instead of taking aldehyde or ketone, we should take this ester. You can see here we broke this bond, these two bond, so that there will be positive charge here. Positive means finally synthetic equivalent. What we can get, this ester we can get, and this is your Grignard reagent. So one of the reagent will help to remove this OMe. Okay, it's ETMGBr. If it is considered negative charge, one will help to remove this OMe, and what will do another one? So the another one, okay, ET. We are getting pH, right? So another ETMGBr, it will attack just here, and you will be getting this OH. Huh? So in this way, you need to choose a ester instead of normal normal aldehyde over here. Now, this is a very good example over there. You can see this is your starting material. This is your target molecule over here. Now, this is a simple 6-member ring. In general, it is said that you should not break a ring. In general, it is not like that you should not break always. Depending on the whatever your target molecule, you can choose whatever you want to do. Now, this is your target molecule. It is said that you should not break this 6-member ring. Then what to do? Let us break this one. If we break this bond, what we are getting? A ketone we can get easily, and this PHLI or PHMGBr you can take. PHMGBr you can take. Now this is over. This problem is solved. Now how we can get this NME2 over there? This is not very easy. So what you should do, just take a compound where there will be a double bond, and then it will be a Michael addition, 1,4 addition reaction with this amine. Okay, so if you treat this dimethylamine with this alpha butyrated ketone, okay, then we can get this product. Then if you treat this one with this phenyl lithium, or you can get this target molecule over here. Okay. Now come to the carbonyl compound via CC disconnection. So you know that how carbonyl compound is formed via oxidation of alcohol. Carbonyl compound in general is synthesized via the oxidation of alcohol. Okay, so this is your keto. So what we should do? Functional group interconversion. So just we should take one alcohol. This is alcohol. Alcohol means again what we need to do? We need to break this bond, right? We have seen. So if we break this bond, what we are getting? We are getting these two starting material. Anyway, you can again synthesize from here all these things. That is different issue. You can choose it by yourself. But in general, we are taking these two start. Once we take these two starting material, it will attack easily over there. You will be getting this alcohol, and if you treat this alcohol, or you can do the simple Swan oxidation. Okay, if you do the Swan oxidation or many oxidizing agents are there, Jones reagent and all, you will be getting this product very easily. Okay, so now in the carbonyl compound, if you wanted to synthesize a carboxylic acid, so in general there are two processes people are following. One is this carbon dioxide process. Carbon dioxide process means this is your alkyl bromide. This alkyl bromide may be converted to this alkyl magnesium bromide reagent. In the presence of carbon dioxide, it will convert to the acid, carboxylic acid. Okay, now in the presence of H plus ion, you will be getting this acid. It's a simple thing. Now there are other processes that if you have cyanide, you can treat this cyanide with this alkyl bromide. You will be getting this cyano compound. Okay, and now if you do the hydrolysis, you will be getting this acid very easily. Now if you wanted to synthesize this tertiary alkyl acid, you should not follow this method. It's mentioned here. I mean, it's a common thing. It's not followed. Why? If you are using cyanide method, there is a high probability that there will be a elimination product also. So cyanide will attack here, take the proton from here. It will be a double bond will form over here, and you will be getting this product like that you will be getting. Okay, so for the synthesis of tertiary alkyl acid, cyanide method is not followed, but in general for the synthesis of carboxylic acid, you should choose either either carbon dioxide method or cyanide method. Okay. So here is another example. So for allylic and benzylic acid or ester synthesis, cyanide method was followed. Okay. So for the synthesis of this allylic or benzylic acid, this method is good. Yeah, they have seen. Actually, in most of the cases, it is not very easy to synthesize the Grignard reagent. Remember this one. Okay. To follow this method, you need to prepare this Grignard reagent. So in many cases, Grignard reagent preparation is not very easy. So for that, you can choose the cyanide, but again, cyanide is also not very good for our health. But anyway, whatever the process or whichever process will be comparatively better in terms of yield, in terms of convenient use, okay, you should choose that one. So okay, for this allylic and benzylic acid or ester synthesis, cyanide method is followed. But for the aromatic compound, CO2 method is preferred as aromatic substitution reaction is not a good option. Okay, so yeah, so why it is said that aromatic substitution reaction? So basically, you can see that if it is bromine, if you are reacting it with cyanide, so it is kind of aromatic substitution reaction, right? So basically, we should not follow aromatic substitution reaction. Then it is better to choose this Grignard reagent to synthesize this acid. Okay. So how to synthesize this one? First, they have taken this NH2 followed by this. You know, this is a Sandmeyer reaction, huh? And then yeah, then followed by this Grignard process, and in the presence of carbon dioxide, you are getting this product. Okay. Now carboxylic acid is over. Now alkenes. Alkenes are the one of the most used one of the most used one of the very good reactive functional group in organic chemistry or anywhere. This alkene is widely used almost everywhere. It's really very important. So how to synthesize this alkene? It is basically synthesized by the alcohols. Okay. So dehydration of alcohol means you have one alcohol over here. If you use any dehydrating product or if you heat it, it will be taking hydrogen from here. Okay. So water will go and it will give you this product. Now how to get this alcohol? We have seen alcohol can be obtained by the treatment of ketone with the Grignard reagent. We can get it. Okay. So this is the way in general alkenes we are getting. So now this is suppose one of your target material. How to get this one? So obviously we can break it over here. If we break it, we are getting OH over here. OH you can get it here, or OH you can get it here. Anyway, we'll see that later. Then which bond we should break? It's better to break this bond. Then what we are getting ketone over here. Then by using this Grignard reagent, we can get this product very easily. Or what we can get, or suppose instead, okay, or suppose if you are taking the OH over here, okay, then what we can do, two pH MgBr. So what it is mentioned, you just take this, you just break these two bonds, okay, then what will happen, this ketone, yeah, it is mentioned here. So as I told in one of our previous example, in this alcohol, if the two functional groups are same, you can choose this process also. Okay. So anyway, any process you can choose, does not matter. Just check which one is the low cost, which one is convenient to use. Okay. In general, to synthesize to prepare this pH MgBr is not very difficult, and this compound is easily available. Okay, benzophenol. Okay, but anyway, both the process will give almost equal product. And here it is mentioned that dehydration process will be rapid, will go through ion mechanism. So basically, this dehydration process is very fast. You can see here ion mechanism means a positive charge will be generated over there. Okay, followed by hydrogen abstraction. So H+ ion will be highly stable. Both side to phenyl groups are there. So it is said like that. Now, if you want to synthesize this product, so as I told you, it is always better not to break the or not to disconnect the ring first. So here is a double bond over there. So we should make a wedge over there for dehydration process. Now how we can get wedge over? Just wedge over here, just break here. Now if we break it here, getting one ketone and one vinyl magnesium bromide. So if you treat this vinyl magnesium bromide with this ketone, we'll be getting this product very easily. Now after that dehydration, it's not a big deal, you can get it very easily. These are some small thing you should remember. Okay, now one of the mostly, or you can say widely used method to synthesize alkene is Wittig reaction. You are studying this reaction from your 10+2, and from in masters as well as in research, everywhere this method is widely acceptable and widely used. Okay, this Wittig reaction, and once this what is that? Once this reaction was first developed by the respective person, okay, this method was used almost everywhere for synthesis of alkene. This is very easy, very selective. That's the main thing. And whatever the whatever the double bond you want, you can synthesize by using corresponding starting material. Okay. So what is this one? If it is Wittig, so consider, there is a double bond over here. You should break. You are breaking. What we should get? We are getting one aldehyde and one phosphorus ylide. You know what is phosphorus ylide? Now, how we can synthesize this phosphorus ylide? We can synthesize it from the alkyl bromide and triphenyl phosphine over there. If we react with this to each other, and obviously butyl lithium is needed, then you will be getting this one. I think you all know the mechanism for this Wittig reaction. It will be going through a 4-member transition state. You will be getting this product. Now consider this is your target molecule over there. So what to do? Double bond is here. Let us disconnect here. Now if we disconnect, there are two ways. Either we can take this one as ketone, this part as ketone, this part as ketone or aldehyde, whatever you say, this one. Now if you take this part as ketone, then it will be your phosphorus ylide, rest of the part, or it is vice versa. Now in both the cases product may be formed, but it is said that the route A is better because this cyclohexanone, it is easy to handle, or you can say easier to handle than this formaldehyde. Why formaldehyde people generally in general want not to prefer? Because formaldehyde cannot stay in its own form. It is staying in polymeric form. Okay, so either you should keep it in mixing with water and very reactive. If you buy any formaldehyde solution, you can see there is mentioned paraformaldehyde. Like way, you can see this is a double bond you want to synthesize over here. This is your target molecule. Now, if we consider our previous method like dehydration, where we should put the double bond, suppose we put the double bond over, where we should put the OH over here, hydroxyl group, we put the hydroxyl group over here. Now, if we do the dehydration, what product you will get here? The double bond may form here, right? Double bond may form here, or double bond may form here. So there will be a selectivity related issues. So okay, so to overcome this problem, we should follow the Grignard reagent. We should follow the Wittig reaction. So that you can choose this aldehyde, or you can choose this part as ketone or aldehyde, whatever you are getting. Okay, and now you will be getting product in very good yield. Both. Just excuse me. Hello. 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 Okay. So now if you follow this Wittig reaction, then you will be getting this product in very good yield following both the two process. Okay. Tell me. Phone money. Acha, okay. You just put it there in my box. Huh? reaction. Only one. Okay. Okay, sorry for this disturbance. Anyway, okay. So now come to the stereoselectivity and Wittig reaction. Okay, so Wittig reaction is very important in terms of selectivity. Suppose this is your target molecule. You need to synthesize this compound. Then what we'll do? There is a two double bond over here. We can break it here, or we can break it here. Now we are getting this terephthaldehyde, both side aldehyde, and this is your phosphoracylide. Or in opposite way, you can take this as a phosphoracylide and this is as your aldehyde. Now in both cases, both these two compounds are stabilized ylide. Okay, and we know that stabilized ylides are providing trans alkenes and are giving cis alkene. So if you have studied this Wittig reaction, you know that one. That remember, stabilized ylide is giving trans alkene, and unstabilized ylide is giving cis alkene. Okay. So what is happening out of these two reaction? Okay, out of these two starting material, people used to accept, or people used to do this. People used to take these two compound as the starting material. Basically, use of this terephthaldehyde is somewhat easier. It is actually, you can get it in cheap. Okay, and the cost of this compound is not very cheap. Okay, it's somewhat very high. That is the thing. And I would say this compound is much more stable than this one. So it is better to follow this method. Obviously, you can get this product through this method also, but whoever has reported, he chose this method over here. Anyway, so this is another example. This is very good example. You can see this is the target molecule. So this is epoxide, right? In this epoxide, and these two hydrogen are in the cis position. So and cis position. So and epoxide, how we can get from the epoxidation of alkene. Okay, from the epoxidation using MCPBA. Okay, using MCPBA, you are getting this one. So obviously, we will be disconnecting to a alkene. We are getting this alkene. You can see these are cis. So we can break it over here, and then we are getting these two compound. I mean these two precursor to synthesize this product. Now what we are getting, if you are treating this with this molecule, we will be getting this one. So this is a unstabilized ylide. How it is unstabilized ylide? What is this ylide means for? What? PPS3. So there will be a positive charge, and in general there will be a negative charge over there, right? And if it is coming there like this, it will be a double bond in general. Okay, so you can see here, this is full alkyl group is there. So alkyl means it's giving electron, right? So it is very much unstable. But in this case, what is happening? If there is a negative charge over there, you can do this is electron withdrawing, this is also electron withdrawing, this is stabilized. So if you see the stereochemistry of this reaction, you can easily understand how this cis product is forming, how this trans product is forming. So as this is unstabilized, it will be giving you this cis alkene. Okay, so this is the simple process how to synthesize this one. You can take this alkyl bromide in the presence of triphenyl phosphine, you will be getting this one. Okay, followed by, if you are using n-butyl lithium, it will abstract the proton from here, then the negative charge will be coming over here, you will be getting this product. Followed by simple Wittig reaction, will be giving you this product. Okay, now we should consider the chemoselectivity in electrosynthetic analysis. Okay, so I mean we should consider various problem. Okay, there will be various problem, but how we can overcome? At least we can see this problem can arises. Now, how this chemoselectivity can arises? Suppose if there are two reactive groups present in a molecule and we want to react one of them, chemoselectivity arises. So in this molecule, there are two nucleophile, right? Oxygen and nitrogen. If you are treating it with acetic anhydride, Either you can get the COCH3 over here, or you can get it over here. So there is a probability of chemoselectivity. Now suppose here is two OH group, exact identical, okay, similar, exact similar, but you want only one group to be alkylated. Although you are using one equivalent, but it is somewhat not very easy. Some amount of this OMe group also you can get. I mean, double methylation also you can get, okay, some amount of. Now another, when the functional group has the ability to react more than once, but we want only single step reaction. Suppose with this sulfide we are treating with this alkyl bromide and we are getting this RS minus. Here is another negative charge, it can react with this RBr to give this RSR, okay, but we want only this product, okay, but we are getting this one also, but we want this. So in this case also chemoselectivity arises. So how to overcome this problem? So guidelines for chemoselectivity. So the thing is that when two reactive groups are present in a molecule, the most reactive group always made to react alone. So we should choose the reagent or the condition such a way that only most reactive group will react first. So consider this is your target molecule. Okay, now this is COO. So CX disconnection we need to do. If we disconnect here, what we are getting, we can get it OH. Okay, so consider this OH as a living group like that, and this OH. So once this is not a big problem, this is a totally different compound. So our concern is this one, how to synthesize. Here is ether functionality and one is considered its acid functionality obviously. Now we need to break here. If we break here, what we are getting? We are getting this OH, COH containing this aryl compound and this iodocyclohexane. Okay, so cyclohexane iodide we can say. Now once we treat these two compound, there is one nucleophile. This is also OH is there. Where it will react? Now in alkaline solution, means it is mentioned here in pH 10, at pH 10, okay, the phenolate ion is much more reactive. This is much more reactive than this acid group, so that this group only react with this one. So we should choose such a condition or such compound so that there should not be any selectivity related issues, and even if there is any issues as there, that could be very less. Suppose if it is OH is reacting with this iodine, but the product may be 2 to 3%, that is okay, that is not a big deal. So once it is reacting with this iodine, iodine, if you are getting this product, your other problem gets solved, right? You can change this from OH to Cl by using thionyl chloride. If you are doing research, you can know by using thionyl chloride, you can do it easily, and then followed by you can get this product. Okay. Now guideline 2. When one functional group can react twice, the starting material and the first product will compete for the reagent. The reaction will be successful if the first product is less reactive than starting material. What does it mean? Suppose here this is your target molecule. Okay, so this is your target molecule. What we should do? Let us break it here. So once we break it here, what precursor we are getting? We are getting this precursor and this one. Now how to synthesize this one? We can synthesize this from these two starting material, right? Now that thing is that once you are treating this the anion of this benzyl alcohol with this phosgene, we are getting this product. Now you can see in the reaction mixture, this is also COCl, another phosgene is also there, COCl2. Now out of these two compound, okay, this is more reactive, so that what is happening, this reaction is going to complete to give this one. Otherwise what will happen, it can react with this carbonyl group also, right? And it will give you pH, so it can react with this molecule to give this product, but it is not giving because the starting material is much more reactive than the product over there, so that another starting material is not reacting with this product to give this one, but instead it is reacting with this one to give you this product. Okay, so similar way, if you want this starting material, suppose you want this one from this sulfide, what to do? What to do from this? So we just want only RSH, not RSR. So we should treat this RBR, alkyl halide, with this thiourea. Once you are reacting with this thiourea, we are getting this isothiuronium ion. Once we get the isothiuronium ion, it can be easily separated out from the reaction mixture. And once we separate it out, you can treat it with sodium hydroxide. Okay, and you will be getting this thiol very easily in addition to this urea. Okay, so this thiol you are getting, and also you are getting this urea over here. So in this case, you are getting only the product what you want, not this not this thioether. Okay, so this is the thing you need to remember. So this is another example over here. You can this is thioether, so you can break it here. What you are getting this these two starting material, and again this SH you can synthesize. There is a different way. This is not the matter of we no need to think about this much too much here at this moment. Anyway, this is a process. So okay, so here what they wanted to say that this is by using thiourea they used this compound. Okay, so rest of the thing we no need to take, no need to see at this moment. So by using thiourea you can synthesize this one thiol. Otherwise you can get the thioether related product, different product. Okay, so this is another guideline for to overcome chemoselectivity related issues. One of the two identical functional group may react if product is less reactive than starting material. Okay, now the thing is that suppose you want to synthesize this one. In general, it is synthesized from this dinitrobenzene, dinitrobenzene, and this is NaSH. NaSH is one of the good reducing agent. This is particularly very selective. Actually, you cannot find anywhere the sodium sodium sulfide, sodium hydrogen sulfide is used for reduction purposes. Very less number of examples you will be finding. So one of the very good example is this one. Okay, so this product is very so this is used to synthesize selectively reduce only one NO2 group. Actually, what is happening? You can see here one of the two identical functional group may react if product is less reactive than starting material. So once this NO2 group comes over here, okay, it will not allow this NO2 to reduce again, as this is somewhat electron donating group. It will not allow to electron transfer all these things, whatever is the mechanism. Basically, it is going through the single electron transfer mechanism. So it will not follow that process. Okay. So this is one of the guideline. Now guideline 4. So this is really interesting. I am feeling everything is very interesting, so I am telling all the things interesting. Anyway, a more reliable method with two identical functional group is said to use a derivative which can react only once. Okay, so you can see here, suppose you need to synthesize this product. Now if you synthesize this product directly, suppose you want to synthesize this one directly over here, can we able to synthesize? It is not possible. If you are using MuOH and H plus ion, some of the you can get both will be methylated or single will be methylated together. So what you need to do, you need to make the anhydride of this succinic acid. Okay, after heating by other process. Now once you get this product, you can easily treat it with methanol. If you treat it with methanol, you will be getting only this product, and once you get this product, you can use thionyl chloride. You can get only this product you can get very easily. Okay, so in okay, so you can get only this product. Okay, so now again this is your fungicide final molecule. Now if you are treating this one, this benzene with this succinic anhydride, what you will get? You will be getting directly it will attack through this over here in the presence of aluminum chloride. So it is that Friedel-Crafts reaction, you know, and you will be getting this product very easily. So another one is guideline is guideline 5. So it is said that when two groups are nearly equal but not exactly identical, avoid attempts to make only one of them react. Suppose you have this molecule and you want only this OH to be methylated, but it is in general not possible, because once you wanted to methylated this one, or in this case also suppose you want to methylated this one, it is not possible. Both of these OH methylate will methylated, or this one or this one, so you will be getting all three products. It is almost impossible. So if you perfectly need in a single reaction a single molecule, just avoid this type of reaction. Don't go for this one. You can choose some other method. So this is the one of the guideline. So wherever you can see that this is not possible, you just don't follow that one. Okay. Now let us discuss the examples of retrosynthetic analysis of different types of compounds. Okay. So this is 1,3 and first let us discuss 1,3 and 1,5 difunctional compounds. So 1,3 difunctional compounds. So if it is 1,3 difunctional compounds, what we need to do? We need to obviously break the bond that is near to CO group. So this is the ring. We must break somewhere here or here. Anything you can choose. Suppose if you are breaking it here, what starting material we are getting? This is we are getting acetophenone and this ethyl acetate. Okay, ethyl acetate we are getting. Now if you treat this acetophenone in the presence of the sodium ethoxide and then treatment with this compound, we will be getting this product. So similarly, if you are breaking here, suppose if you are breaking here, what we are getting? PH COOET, it is a leaving group over here, plus CH3. Anyway, you can follow this process also, no problem. Okay, anything you can follow. Now you need to choose different way. Consider this is your one of the target material. This is very interesting. If you break it here, what will happen? You will be getting one of the compound is this one. It is very understandable to you, right? Another one you are breaking, so one leaving group should be here. You are putting one leaving group here. This is OET. Now you can see both these two compounds are same. So you no need to use two different compounds. From a single compound, you are getting this target molecule. Just consider you are breaking it here, A. So what starting material will be getting? OET plus CH3. Okay. So from these two starting material, you are getting one product, and but here from one starting product. So which one you will choose? Obviously, you will choose the method which will be giving you the same the product from the single starting material, not from the two different starting material. So you can understand the difference. The where you will be you will do the disconnection. Okay, where you should not do disconnection, there is a difference. Okay, so in the same way, this is an example. This is a target molecule. So wherever where you can disconnect, you can disconnect at A, or you can disconnect at B. So at A, what will happen if you disconnect? You will be getting this starting material and this starting material. But if you disconnect B, it is always said that you should not break the ring if possible. But here it is happening, you must break the ring. Why I am telling you? If you are breaking at B, you will be getting this starting material. This is single. Now this is again 1, 2, 3. 1,3 dicarbonyl compound. You can break it here. You will be getting. Once you treat this with this compound, okay, this is easily available, and yeah, this is also available. Maybe cost will be little higher. If you treat these two, you will be getting this, and followed by you will be getting this product. Now through A, the problem is that you need to synthesize this product also. The cost of this indene-dione, this compound is known as indene-dione, 1,3-dione. The cost is very high. So you also need to synthesize this one, and for to synthesize this one, you must follow this. Okay, plus Et. Et. So if we consider the whole scenario, then this process is much easier. Okay, so you need to follow this process to synthesize this one. It is not shown here, so it is better to follow the route B instead of route A. Now here this example, you can see here, if you don't break the ring, you can get these two starting material, okay, cyclopentanone and this diethyl carbonate. But if you break the ring, what you will get? This one. This is called, you all know, adipic acid, ester of adipic acid. Okay, so ester of adipic acid, or you can say that adipic acid you can get very easily. From adipic acid you can synthesize the corresponding ester, followed by you can react to give this compound. So route B is much better in this case. It is it is giving a symmetrical and readily available diester. Okay, so in this case, this you need to break this bond. You need to break this bond means you will be getting a starting material which is easily available, and the process is very cheap. Okay, so this is an beta hydroxyl carbonyl compound. So we have seen 1,3 dicarbonyl compound. I think I can take another 5 minutes, then I will ask for. So if you break it here, you have this molecule. If you break it here, what will happen? So you will be getting these two starting material. Now you can see here that these two starting material are same, not different. Okay, you just put this bond instead of here. These two starting material are same. So you should disconnect in such a way, if it is possible, you can get the same starting material. So this is another example. This example I have taken from Claydon. I think you can understand. So this is a gingerol. We should break here. If we are breaking, what starting material we are getting? You can see here positive, negative charge, aldehyde we are getting over here. So once we get the aldehyde here, they have mentioned the process. It's simple. They have mentioned. So we need to use n-butyl lithium. Okay, if you use n-butyl lithium, it will abstract the proton from here, and then it will attack. It will followed by attack here, and we will be getting the product. Okay. So okay, you can see here the two starting materials have been used. N-butyl lithium. Two reagents have been used. Two base, n-butyl lithium and lithium. Lithium diisopropyl amide, LDA. So this is very interesting. What is happening here? So butyl lithium is taking the proton from this OH. Okay, first it is taking the proton from this OH. Once this proton abstraction is over, this LDA is used. LDA is taking proton from this CH3, and then it is attacking over there, and we are getting this product. Okay. Just let me. Time is very short. Okay, so let us discuss 1,5 dicarbonyl compound. So in this 1,5 dicarbonyl compound, to synthesize this type of compound, we should follow the we should cleavage the alpha beta bond in a reverse Michael addition. Okay, so here you can see here we are breaking these two bond. Then what we are getting starting material? If we are making a double bond here and a simple bond here, so if we are using a base, it can react here and we'll be getting this product very easily. You can see here nicely. So how to synthesize this compound? You can see this is CH3 only. It's active methylene group, but to increase its acidity, or to increase the acidity of this hydrogen, we need to put a electron withdrawing group over here, COOET. Now if we use COOET, this is the active methylene compound here. If you are using a base, it will abstract the proton from here, then it will attack, followed by, if you are using hydroxyl group and heat in the presence of H+, you will be getting this product very easily. It's very simple, nothing difficult. Similarly, if this is your starting material, 1, 2, 3, 4, 5, this is again is your starting material. So what are the things you are getting here? You can see here, you can break over there. Then if we break it, what you are getting, CH2 minus, and this is double bond alpha beta unsaturated ketone. This is here. It is also going through the Michael addition. So this is your synthetic equivalent of this compound. Again, it can attack here. You will be getting this product. You can see this is the synthetic process. Okay, so this is another example. This is a very nice example over there. 1, 2, 3, 4, 5. This is also again 1,5 dicarbonyl compound. So in this 1,5 dicarbonyl compound, what you need to do, as I told, that Michael addition. So you can break the bond here. You are getting double bond over here. Now the problem is that this double bond, obviously you cannot get this compound very easily, right? You cannot get, you need to synthesize this. How to synthesize? Cyclohexanone and this formaldehyde. Now even if you react these two compound, you may get this product, but formaldehyde is very reactive, and even this molecule itself, so it may give you some other product, or the yield may not be very high. So what people are doing in many cases, they are keeping this compound as manic base. How? Just treat this compound with this formaldehyde and this dimethylamine. It will give you this compound, and this compound is very stable. And again, you can keep, then what you can do, in the presence of methyl iodide, you can treat this with methyl iodide. You will be getting this product. Okay, so obviously I minus will be there. Once you are getting this compound, you can treat it with this compound. Okay, this is this is a yeah, this is a active methylene group. So you can take this molecule and attack here. It can attack here very easily. Okay, so in this way it can be moved out. One is this one condition. Another one may be, if you are hitting it, the proton will be coming out from here. It can go out, then it can attack here to this double bond and going through the Michael addition. I think it is understandable to all of you. So most of the cases this is not very stable, or this or even it can give very less yield. So that what is happening, people are doing this manic reaction with this manic base, that treating with this active methylene compound to get this product. Okay, so this is another example. I think I should stop after this. So this is one target molecule over here, you can see. So how to break this one? You can see it's a double bond. Let us break it here, and again we can break it here. So what molecule you are getting? Once we break it here, we are getting CH3. So yeah, this is 1, 2, 3, 4, 5, right? This is 1, 5. So this is ketone. So now we need to think where we should make the double bond, where we should break. Let us break it here, and we should make a double bond over here. You can see. Now if you are using NaOET, sodium ethoxide, this is a base. Okay, so which one is your most acidic? This one, right? So this will be abstracted and it will attack here, and followed by, again through this you can get this product. Okay, I just supposed to, okay, just let me discuss this part, then I will finish. Actually, okay. This is the cross condensation. There are many with the same molecule you can do condensation to avoid many problem, but it does not. You remember that whenever you are going to synthesize some molecule, you don't have that much flexibility that whatever you want you can choose. Okay, somebody suppose give you some compound to synthesize this one, and for that one you may need to do cross condensation. So this is one of the example. It is mentioned that use of compounds that cannot enolize. So you should use such a compound which cannot enolize, or you should disconnect in such a way that one of the starting material cannot enolize. So once you disconnect here, okay, you'll be getting this starting material, and this is another starting material. So only this can enolize, this cannot enolize, right? So you can choose these two reaction, and yeah, these two reagent, these two starting material, in the presence of this base, you can get this product. In the similar way, suppose this is your starting material, this is a target molecule. Now you can break at A or at B. If you are breaking at A, what starting material you will be getting? This is A or B, yeah, this compound and this one. Now it will be the substitution reaction, aromatic substitution reaction. Okay, and we know that we should not we should avoid aromatic substitution reaction, and in B what we are getting these two starting material. Now this you can do easily in the presence of any base will abstract the proton from here, will attack there, and you will be getting this product. Now these two example is really interesting. You can see this is your target molecule. Okay, here is a double bond. If you break it, what we can get? We can get a double bond over here. We can get. We are breaking the double bond. We are getting CH2 and CHO. Okay, CH2 and CHO we are getting. Now it's a simple condensation reaction, right? So that you can get this product very easily. Now you can see if we use base. If we use base, and there are two active methylene groups are there, one is CH3, another one is CH2. So if you are use base, kinetically controlled alkene or enol will form, kinetically controlled. So which one is less substituted? So for base, this one, proton from this one will be abstracted, and this enol. This is kinetically controlled, remember, and with acid, you will be getting thermodynamically controlled enol. So thermodynamically controlled means this one. Okay, so this is thermodynamically more stable than this one, that's why it is thermodynamically more stable. See here, to condense from this CH2 we must use this acid. You can see here, by using phosphoric acid they can get this target molecule. Maybe in that case they get the condensation this CH3 also, but the product is maybe very less. In the same way, you can see this example, you can break this molecule here. You are getting this starting material along with this starting material. So in this case also there are two active methylene groups are there, one is this one, another is this one, but in the target molecule it is attached through this carbon. So this carbon means this is less hindered. Less hindered means it is kinetically controlled condition we should use. So kinetically controlled means we should use base. So you can see here, if you are using base, you are getting this product. So base, remember, in general, for kinetically controlled product enol formation, we should follow that LDA or very bulky, very sterically crowded base we should use. Lithium diisopropylamide, like that base we should use. Okay, or you can use dibal and all these things. Okay, I think sir, there are many slides are there. I think we can stop it today because 3:30 is last time. So thank you very much, and yeah, please, if you have any question, you please let me know.
Sir, good afternoon, sir.
Please tell me.
My name is Vandana. I am a PhD scholar from Bharathiar University, Department of Chemistry. Thank you for your very elaborate presentation on retrosynthesis topic, sir. I just had a small doubt on the topic where you discussed about 1,3 and 1,5 difunctionalized compounds. Yes, sir. In this, in one slide, you told about starting the same. If from one starting material itself, we can get the product. That method. This one, sir.
This one. Okay.
This one. We in this you told from the same starting material itself, we can get the product that we desire. But here in this case, we have still one more active site where the intermediate can attack. So we may not stop at the target compound, but still it may lead to a trimer or so. Is there any possibility, sir?
Yeah, just tell me again. I cannot get you. So that you are telling that okay, we get this product, then?
Yes, sir.
Acha, okay, then you are telling that, acha, okay, so there is another CH2 active methylene is there, right? In this CH2.
Yes, sir.
So this
Yes,
also
sir.
can react.
Yes, sir.
Yeah, that is possible. That is obviously possible, but in that case, we may need to use some harsh condition. Remember, okay. Okay, so that whenever we are doing the reaction, what we even we should check that whether one spot is formed or two spot is formed. Whenever we are checking that, okay, so one spot is formed, it may be our product, we just stop the reaction. we cannot continue the reaction for infinite number of infinite hours of time, so that the
Yes,
reaction
sir.
will continue at equilibrium. Okay.
Yes, sir. Yes, sir. Thank
Okay.
you, sir.
Okay. Thank you. Any other?
One more question is there in the chat box, sir. Is
Okay,
it possible? Is it possible to apply disconnection approach into carbohydrates? That's a question, sir.
that may be possible. I don't have that much idea about carbohydrate chemistry. Frankly speaking, I don't have that much idea, but that may be possible. I am not sure there.
Thank you, sir. Thank you so much.
Yeah. Thank you. Yeah. Any more? Is it possible to apply disconnection approach into carbohydrates? Okay. Yeah. That dear, I am not 100% sure. Okay. So I just don't want to comment on that. I need to check. Any other?
In the absence of any other question, I do thank Professor Dr. Ganesh Nand for his excellent presentation and sharing about retrosynthesis to our audience. We are especially thank you for accepting our invitation in the last minute, and generous acceptance is been appreciated, Dr. Ganesh Nandi sir. Once again, on behalf of Bharathiar University Chemistry Department and the organizers of this recent Trends in Chemistry 2021, we do thank for your valuable time and sharing your expertise with our audience. Thank you very much, Professor.
Okay, thank you very much, Professor, for inviting me. And whatever I have to share with you, I have shared. And anyway, if you have any questions, you can send to my email ID. Okay, I think some other questions people have told. Okay, no, there is no more questions. Okay, thank you, Professor. Thank you for this invitation.
Thank you.
Please, Professor, please join our validation.
Okay, now is it now or?
Now it's going to start. Just 5 minutes.
Okay, no problem.
Yeah.
Okay, no problem. Thank you.
Dear delegates, please wait. We are going for validity address. Okay. Dear delegates, one announcement. Once finished this webinar, we are going to issue your participation certificate within 20 working days. We will send all the certificate through your email IDs. Okay. After 20 days, if anybody not received our e-certificate, please remind us through email. Also, please wait some 2 or 3 minutes. Now we are going to open our validity function.
ஏற்கனவே பே பண்ணியிருக்கேன்.
Dear delegates, please wait 5 more minutes. After 5 more minutes, our registrar will join. Vandana.
Sir.
Can you sing me some song prayer?
Sir.
ஒரு பாட்டு பாடுமா.
Sir, prayer song. Let us start with a prayer song. Dhanam tarum kalvi tarum oru naalum தளர்வறியாமனம் தரும் தனம் தரும் கல்வி தரும் ஒரு நாளும் தளர்வறியா மனம் தரும் தெய்வ வடிவம் தரும் நெஞ்சில் வஞ்சமில்லா இனம் தரும் தனம் தரும் கல்வி தரும் ஒரு நாளும் தளர்வறியா மனம் தரும் தெய்வ வடிவம் தரும் நெஞ்சில் வஞ்சமில்லா இனம் தரும் நல்லனையெல்லாம் தரும் நல்லனையெல்லாம் தரும் அன்பர் என்பவர்க்கே கனம் தரும் பூங்குழலாள் அபிராமி கடை கண்களே அபிராமி கடை கண்களே.
Dear delegates, anyone want to give your feedbacks?
Dear delegates, please, if you want to give any feedbacks over here, please unmute your audio and give your feedback, valuable feedback, so that we will improve our next webinar.
Overall feedback is fine.
Dear, anyone?
Professor A. Ramasubbu,
Hello, Professor. Good afternoon.
Yes, sir. Please give your valued feedback. Professor.
Hi.
Hello, Professor. Please, we are expecting your feedback.
Good afternoon, professors.
Problem,
Yeah,
sir.
Good afternoon, Professor.
4 day seminar was really wonderful, excellent, especially the first one given by the talk given by the professor from Materials Research Center, IAC. The ma'am has given a wonderful lecture on basics on photochemistry and photophysical aspects, and especially with the various compounds on second generation and third generation thing of photosensitizers, and improving the quantum yield from 5% to 24 to 30% on some kind of compounds. Really, it is wonderful things. However, I had some. I thought of raising some questions, but unfortunately, due to want of time, I couldn't ask that thing. But all the things and the synthetic procedures and everything was excellent. And a similar manner, the next day also, the afternoon session by the IIT professor also very good. And the next day also related to some kind of zinc oxide with molybdenum sulfide and graphene oxide nanocomposites for various environmental applications and energy applications. Everything was found to be excellent, and they have given a wonderful treatise to the audience. Especially we people have benefited a lot from your say webinar, and we are very much grateful and thankful to you for giving us a wonderful opportunity to join and to learn something new on these aspects. And in the similar manner, yesterday also the talk was excellent, and especially the cobalt catalyzed organic synthesis by Professor Bhaskar from IIT Kanpur or somewhere else. And he has given a wonderful thing among all the lectures. All of them are excellent. Even then, I could rank that lecture as the number one, because she has given the professor has given a wonderful treatise from basic to the advanced level. Even the professor has compared the conventional synthesis, and then with the abnormal, what is that, the rational synthesis using the cobalt catalyst things. And the way he has compared with the cobalt with other metals like noble metals, the castways and other things, and then the new aspects, in what way the carbon hydrogen activation and carbon carbon bond formation, etc. It was really amazing, and all the things that he was supported with all the latest publications, especially his own publications. And finally, the related to solving the environmental problem, like what is that, the degradation using the cobalt catalyst things about plastics to some kind of polylactic acid or something, like some derivatives like that. Lactic acid derivative, though it is here it is given mentioned that it is a patented one, but it gives a wonderful insight, and also it gives an opportunity for the youngsters and the next generation people to learn new things. What are the areas, what are the newer vistas in chemistry that is possible. In this aspect, I am really much thankful to the organizers. And today's lecture also, retrosynthesis analysis, I'm really sorry that I couldn't attend the morning session due to my own commitment to my class, but the afternoon session was excellent. Retrosynthesis, I'm very much thankful. Good afternoon, Professor.
Dr. Salian.
Thank you, sir. With this, I would like to conclude myself. Thank you.
Prabharan, sir. Thank you, sir.
Okay.
Good afternoon. Happy New Year.
Happy New Year, sir.
Happy New Year, sir. Thanks a lot for your feedback, sir.
Okay, sir. என்ன செலியன் ஆரம்பிக்கலாமா? சார் ஆரம்பிக்கலாம் சார்.
Yes, sir. Welcome, Rasul. Sir, now we are going to
சவாலை பத்தி தான் பேச போறேன்.
Good evening to all. Sir, start பண்ணிடலாமா? Sir, shall we start?
Yes, sir.
Okay, sir. Good evening to all. I feel immense pleasure to welcome you all for the valedictory function of RTC 2021, sponsored by Chemistry-Bharathiar Phase 2. Now, I am very happy to welcome our most respected Professor Dr. K. Murugan, Registrar in Charge, Bharathiar University. He has given constant support and encouragement in various aspects. He has 30 years of research and teaching experience. He served as an Additional Director, DRDO, BUCLS, Ministry of Defense, Government of India, and has been the Vice Chancellor of Tiruvallur University, Vellore, Tamil Nadu. He also served as the Vice Chairman for the Tamil Nadu Science and Technology Centers, Department of Higher Education, Government of Tamil Nadu, India. He has done cutting-edge research on synergy among plant-borne compounds with microbial insecticides, nano-insecticides. He has published more than 450 research papers and produced around 50 PhD research scholars. And he guided 15 postdoctoral fellows. He also written 2 books. He is the recipient of many awards for his scientific achievements, including FAO Forest Award, Italy, Commonwealth Fellowship by Association of Commonwealth Universities, CIS TWAS Fellowship, Italy, and also awarded JSPS Fellowship, Japan, along with so many awards in his hand. On behalf of Department of Chemistry, I welcome you, sir. I extend my welcome to our invited speakers, Dr. Sangu Sundaram Saktivel, Dr. G. Prabhu Shankar, Dr. A. Subramania, Dr. Bhaskar Sundaraju, Dr. Venkatakrishnan, Dr. Rajamalli, Dr. Iswaramurthy, and Dr. R. Ranjit Kumar, and Dr. Ganesh Nandi. I welcome you all. Further, it gives me a great pleasure to welcome all the participants for this valedictory function. And also, I welcome our department colleagues. I welcome you all. Once again, I welcome you all for the valedictory function of Recent Trends in Chemistry 2021, sponsored by DST Pars Phase 2. Thank you.
Sir, very good afternoon, sir. உங்கள் அனைவருக்கும் ஆங்கில புத்தாண்டு வாழ்த்துக்கள். Happy New Year 2021. Really, I am very happy to participate in the DST Pars Phase 2 sponsored 4-day webinar on Recent Trends in Chemistry, that is abbreviated RTC 2021, organized by Department of Chemistry, Bharathiar University. At this juncture, I welcome to everybody for this valedictory function, and also I thank our Honorable Vice Chancellor, Dr. P. Kaliraj, who has inaugurated the webinar, and also I thank Professor Dr. P.S. Morgan, has given presidential address for this webinar. He is the syndicate member and former professor and head Department of Chemistry, Bharathiar University. We had a very good time the day before yesterday for our syndicate meeting held at Bharathiar University. And also I thank Dr. Convener, Dr. M. Elanjelian, Head and Associate Professor, Department of Chemistry, Dr. Prabhakaran, Dr. Suresh, Dr. Kannan, Dr. Prabha Madam, Dr. Selvaraju, Dr. Kaveri, Dr. Murugesa Pandian, Dr. Sundaravel, Dr. S.N. Karthi, and also resource persons from various places, India and abroad. And really, it is a very nice webinar for the student community, plus the faculty members of chemistry, teachers, and all over the world, chemistry. Without chemistry, we cannot move. Our body constitute the chemistry in a different tissues, and also our food, day-to-day food is very important. Food is a very important medicine. Recently, our Tamil Nadu government, Department of Health, has done many research work for the COVID-19, and they have discovered citrulline from the citrus fruit has got a very good glide score by docking, in silico docking process technique, and we can take all citrus fruit. And also among the cereals, the ragi is one, so that we can also have ragi as a food in the breakfast or in the lunch or dinner or any time as a ragi malt and all those things. And also, as far as medicine, medicinal plants include, the neem is number 2, then citrulline, that is citrus family. And you can also take neem tender leaf or whatever, maybe the bark or root, depends upon the homeopathy or the doctor's prescription. You can take neem for to get rid of this virus and viral proliferation as well as infection. And food is a medicine. And also you have a lot of banana. You have a variety of banana, red banana, and then green banana, and then many banana variety. Banana is not only a fruit, not only is antioxidant, and also it is a meal. If you have a if you are taking 2 banana in the breakfast, it is a meal. You need not take anything. It has all kinds of nutrients, particularly the red banana, that is in Tamil sevvalai. The banana itself is a good look. The outlook is very nice. The color, it contains a lot of carotenoids and also lutein and potassium and magnesium. These banana, whenever if you are coming to university, we are all taking all oily vada, that is masala vada, and then ulunda vada, and then you see bhaji, valakai bhaji, and then urlakalangu bhaji, and then onion bhaji, so that they have dipped in the oil. We are taking a lot of oil. It gives a lot of problem, and if an older person above 45, it accumulates, and we are getting a lot of heart problem. So that if you take banana, red banana, and you can gain health, use a very good color also. Okay, you will get a very facial good color, attract people, both male and female. Both male and female they can take. And then it cures, it also the lutein present in the banana, which cure the carotenoid, in eye diseases, and a very good digestive capabilities. And also it reduces the blood pressure. So that our traditional food stuff, is really gives a lot of remedies. We have forgotten to take our old traditional food materials, so that we are getting we are going for a lot of fast food, and other oily food, and a lot of meat also we are taking. So that whatever maybe it should be limited. If you are taking meat weekly once, you are taking chicken or fish, like that you have, and then we are neglecting some important fruits also. For example, tomato, takali palam. It gives a very good fruit even if you are going for a 5-star hotel, and we are not taking in for salad carrot and then bellrica and then tomato is there. We are not taking a tomato. Tomato is a very nice food material. Similarly, we are not taking what is that papaya. And then the thing is, whatever maybe we are thinking that the food should be readily available. If you go there, if you go to the in the kitchen or dining room, immediately whatever maybe idli means we will put 3 or 4, or even one idli we are putting very fast, and one dosa means half we are taking very urgently. No, not like that. You have to sit and you have to take. We don't have patient. What is that? Patient in removing skin of other food material like papaya. Inside the papaya, you can have a lot of seeds are there. Lot of mucilaginous substance are there. You can put in your body, and you can have a very good health and skin care and other thing. So that in this juncture, our department is progressing very well. The former head of the department, Dr. Mohan sir, is also has come as a syndicate member. He will give our moral support to the department. Professor Dr. Ilanjalian has taken over the department. He is progressing well, particularly with the associates, with the help of other teachers like Prabhakaran, Dr. Kannan, all other Kaveri madam, Prabha madam. They are all They are all assets of this department. They are all progressing very well. And Dr. Suresh, organizing secretaries, he is the hero, we can say. 2 organizing secretaries, like sometime in the movie, in those days, we have 2 heroes will be there, like Kamala Hassan and Rajinikanth, Kamala and then Siva Kumar sir. And then sometime even in old movie, we can have Dr. MGR and Dr. Sivaji Ganesan also. In Gundukili, they have appeared. It is a very nice like that. Dr. Suresh and Dr. Kannan is a point. They have organized this conference as a very nice, in a nice manner. And then the students, the students of the research scholars, postdoc, and MSc, and other students, supporting staff of the department, they are progressing well, and our university is progressing very well. For all that, our Honorable Vice Chancellor giving necessary support, and also seminar hall for our chemistry department, chairs, chairs, tables, and everything. And in front of our department, they have cleaned everything, and you have a nice corridor, nice departments. So that I congratulate each and everybody for having this seminar in our campus. I think a lot of people, they have participated. And lastly, the feedback has given the government professor, our name and doctor?
Ramasubbu.
Dr. Ramasubbu sir. He is also a very enthusiastic chemistry professor, and he used to say in the morning ground, shuttlecock ground. So I am playing for last 25 years. You see, you have to play like me, like that. He taught very well to me also. I have adapted some technique by taking. Sir, one day I told him, sir, my chemistry in this portion is not working, sir. By taking, he only taught me, you take like this ball, and then you turn and put it in, and then your body will be there in a good manner like that. He is not only a chemistry teacher, he knows chemistry, he knows yoga, like that. Chemistry, yoga, and life, is everything is very nice. I also seen when I was going Tambaram to Nungamagam for my BSc days in those days, 79 to 82. While crossing the Palavaram to Palavandangal, they used to put Adhihalayil Nadi Josiyam, like that. They used to put a board. Like that, I am boring you by saying a different thing. But health is wealth. You have to laugh. Then your body cell will work. If you are freezing your laugh, if you are freezing to talk to your friends, your body cells won't move intact. Then your blood vessels not working, capillaries not working. Then your heart not working. You should good morning. You have to say good afternoon, sir. Solunga. Sir, good afternoon. Good evening. Good evening, sir. Yes, sir. This only we need. You are all very good professors. Thank you very much for giving me this opportunity. By saying goodbye, goodbye, goodbye.
Thank you, sir.
Sayonara. Thank you.
Thank you, sir. Thank you.
Thank you, sir. Good evening, sir. Bye-bye, sir.
Thank you. Bye-bye. Bye-bye. In China, they used to say bye-bye. Bye-bye. Like that. Thank you, sir. Vanakkam, sir. Thank you, sir.
எப்படி இருக்கா? இது நல்லா இருக்கும். அதோட நல்லா இருக்குங்க.
Our respected registrar, Professor K. Murugan sir, thanks for your validity address at your busy schedule. Now it is a time to give vote of thanks and conclude our webinar RTC 2021. Our honorable and respected Vice Chancellor Professor P. Kaliraj, Bharathiar University, and most respected Professor Dr. K. Murugan, Registrar, Bharathiar University, Professor P.S. Mohan, Syndicate Member and former HOD of Chemistry, and Dr. M. Elangelian, Associate Professor and Head of Department, Convener of this webinar. My dear colleagues, delegates, faculties and scientists from various institutes and industries, research scholars, students and friends, very good evening to all. First of all, on behalf of RTC 2021 team and myself, I record my sincere thanks to our Honorable Vice Chancellor and most respected our Registrar for their constant support to conduct this webinar. My thanks and gratitude to Dr. M. Evangelian, Head of the Department of Chemistry, Bharathiar University, for adding new dimension for the successful organization of this webinar RTC 2021. Our special thanks to the coordinator DST per Space 2 program and DST per Space 2 program Government of India. On behalf of Chemistry Department, I share my heartfelt thanks and gratitude to all staff members of Chemistry for their whole support and dedication and teamwork rendered to us. My special thanks and wishes to all our eminent speaker of this webinar, Professor Prabhu Sankar from IIT Hyderabad, Professor Venkatakrishnan from IIT Mandi, Kanpur, and our lead scientist Dr. Saktivel Sarmasundaram, ARCI Hyderabad, Dr. Iswaramurthy from CLRI Chennai, and Dr. Rajamalli, she is our chemistry alumni, IIC Bangalore, and Dr. Ranjit Kumar from MKU, and Dr. Professor Ganesh Nandi from NIT Trichy. From various research fields of chemistry were delivered valuable lecture in this event. I convey my special thanks to all delegates who have participated in this webinar from various disciplines of science across the globe, especially from Qatar, from New Delhi. Overall, we have received 512 responses, in-depth more than 175 delegates are actively participated in this webinar. I extend my special thanks to DST for the funding support. My thanks continue to all committee members, my friends Dr. R. Prabhakaran and Dr. S.N. Karthik, Dr. Sundarvel and Dr. Murugesh Pandian, Selvaraj and Professor M.E. Kaveri, Dr. Prabha and Kannan, Department of Chemistry, Bharathiar University, and research scholars and my research team, Kabirasu, Shyam Sivupan, Amsiveni, Vandana, and Sendamal Selvi, and my special thanks to Mr. Clinton, those who are all technically supported to do smooth conduct the this webinar RTC 2021. I thank all our non-teaching staffs, Mrs. Nitya Kala, Mr. Balamurugan, their support throughout the program. And finally, I want to thank our Bharathiar University IT guy, Mr. Manoj, for his technical support. Once again, I thank all the delegates and our beloved professors and our Vice Chancellor and our Registrar. Thanks to all. Yeah, thanks.
Thank you.
Vandana, you can give announcement, please.
Thank you, sir. Dear delegates and participants, thank you all for your valuable participation. There's an important announcement. We require about 20 days, minimum of 20 days to process the participation certificate. We will arrange to send the certificates through email. In the meantime, we request you to be in touch through our WhatsApp group. Thank you all for your participation. Kindly fill in the feedback form for today as usual. Thank you. Now we are winding up the session. Thank you all for your valuable participation and making this event successful.
Thank you. Thank you.
Thank you.
Thank you to all.
Thank you, sir.
Sanjil Raj Kapoor.
Sir?
Where are you now?
Sir, I'm working.
ஓகேம்மா சரியா கேட்கல நீ தனியா பேசு. Dear delegates, anybody wants to give your feedbacks? We are most welcome.
Dear participant, kindly give your genuine feedback. Then only we will improve our next webinar. We are most welcoming your negative feedbacks, if any.